Okay, so this week's lab is on lenses and the optics of the eye. Um, some announcements. There's only going to be one more lab after this one. So get all the points that you can for the end of the semester and finish out strong. Um, there's going to be a quiz next week. So it's going to be on sort of today's material. And I think the last thing is there's student evaluations now available. So you should see like some kind of pop-up on Canvas. Go ahead and complete those evaluations for this lab. There'll be like questions like how was the lab? How useful was it to you? And I think at the end you might evaluate my teaching. So your names aren't connected to the evaluations, so go ahead and fill those out when you can. All right, let's get to the instructions. So this is going to be a big opportunity for points. This lab's worth 81 points. I don't know why it's 81 and not just 80. But it's not too difficult once you get the hang of it. Let's get to the instructions. So I think this is one of the only labs where we use a different program, a different simulation program. So here at the top, here's some reference videos. They're always helpful. And we're going to be going to this OPhysics website. And here you'll see something that looks like this grid. And on the instructions, you might see like these little, this grid in the back. Actually, let's just go to the thing. So you'll see these squares. Each square is 1 centimeter. So that'll make it easy to 1 centimeter, length. In the website, in this simulation, you can, change the size of the object. It's labeled on the left. You could also change where it is in space and see how the image changes on the other side. So that's real neat. There is a focal point on each side of the lens, and you could change where the focal points are. Something to see as I move this closer to the lens, this other focal point also moves, so it's symmetric on both sides. Okay, so for the first part, let's go to here, down to the first part. You're going to be looking at a convex lens. Those are the ones that look like ovals or like a football. Let's go to that. And you're going to be arranging, or I guess first you're going to be doing a calculation. It says calculate first. And then the next question is confirm. So pretty much, half of this lab is going to be doing this calculation, given this information, and then just checking to see if you're right. So we have this focal length, object distance, and object height. So we'd go into, once you do your calculations, you go into the program, it's right here, and just arrange it however it says and check to see if you're right. And the values are also listed right here. So it should be, step by step, helping you along the way. One thing I will say, for if you write anything down today, if you don't write any notes, I'd at least want you to write this down. So when it says focal length and it has this -4, so it's a little misleading. Focal lengths, this F specifically, I guess we could have changed it to be f prime. So let me put a little apostrophe in there. So this is at -4. So that's one thing I can say to look out for in the instructions. So let me, so for example, let's do this first one. So focal length f -4. We have to read this thing at the top, though. Let me highlight that. Focus prime is labeled in a simulation, should be on the left of the lens. So focus with the apostrophe is on the left. So let's go to the simulation. So focus, there's apostrophe right here. So this should be the one that's on the left. And this is the one that is at -4 right there. All right. Then when we do these calculations, we have to make the distances positive. And so this focal length right here, this regular f, so this is just regular f. Let me show you that. So this is this over here. This should be +4. That's why this is on the right. If you're having problems with this, just let me know. But you think of it as the total distance to the lens for this object distance. So for this one, we're doing just convex lenses with things that look like, with lenses that look like that oval shape. Then we're going to go down to concave lenses. And again, I maybe could have highlighted this top bit right up here. So you could do that yourself. So right up here, highlight this. The focus prime should be on the right of the lens. So let me go in and check. So focus prime, I would then move that over to the right of the lens. And we can see the lens has changed its shape. So now this is a concave lens. Okay, so this is sort of your way to double check. Okay, so now focal length f is +4. Okay. Similarly, you just, a lot of this lab is doing calculations and checking to see if it's right. It's, like I said earlier, with the positives and negatives, not really helping with the instructions. As soon as you get a hang of what you have to do to make the calculations right, then this will flow easier. I've taken down a note on how we could improve this myself. Once we get past that, though, we're then down to optics of the eye. And so we're going to go to this other web page right here. It's the same website, but we're going to look at the optics of an eye. So this is going to be a human eye, and we have this anatomy overlay. You can turn that on if you'd like, or you could turn it off if that's a bit too busy. To sort of do this experiment, first you can, like always, you could just play with it. You can move the object, move the focus, and look at what is changing when I manipulate the focus. So this lens right here, that's the crystalline lens inside of your eye. That's right on the inside of it. It has to change its shape. So it's sort of squeezing itself. It's getting very thin. By doing that, it's changing, the angle that the light strikes the surface. And that means that it's changing where the light is bending. So now, let's go back to where it was originally. So like this is an object that is out of focus. It comes to a point right here, right in the middle of the eye. So in order for us to see something clearly, that object, that point of light, has to strike the back of the retina at a single point. So I would say that object, this dot, is in focus when, let's go right about there. So I would say now this object is in focus for this eye. You're going to learn all about that. These questions kind of, walk you through that. This is for a normal vision. Later, you're going to look at near and farsightedness. So let's do that. So let's reset. And we're going to look at someone with nearsighted eyes. Okay, so this is, an eye that can only see near. Again, the questions and the instructions will walk you through what you need to do. But right here, you can see this little checkbox. It says correct for nearsightedness. So I'm pretty much just giving this person glasses. I'm giving this eye glasses, and it's bending the light a little bit before it hits the lens inside of the eye. And that makes it easier for that lens to bend the light to strike the back of the retina. Okay, so then, correcting for nearsightedness and correcting for farsightedness. At the very end, we have this sort of blind spot. It's, just a test. See what you can see. I'd suggest like making the page bigger so you don't have to get too close to your computer screen. So I go like that, and it says to go like that. It says to cover your left eye and look at the cross on the left of the screen. So once you do that, you're going to move your head either farther back or a little bit closer. And there should be a point where maybe this dot on the right, maybe that will disappear. So for, typical, eyes, there is a blind spot, and it's up to you to try to see where it is. It's just, recording your observations. I think there are a few questions. Put in here that you can answer in your observations. And the evaluation at the end. Yeah. So pretty much a lot of the lab was just doing, where is it? It's a lot of the lab is just doing these. And once you get used to how you have to slightly change these values, it should be easy to, go through, and you can always double check with the simulation. That's also kind of why I want you guys to do, I want you to do at least 2 of these. So it could be any 2. It can be, one from part 1 and one from part 2. But I just want to see you guys do 2 of them, so I know that you know how to change these values. So that's, -4 in the simulation diagram. Right, so I just want to see you do 2 of those. When it says reproduce the diagram, you could just take a screenshot. That's fine. Yeah, so that's all I want to see today, is at least 2 of those things worked out. Let me go over some notes. If you guys haven't gone over this, I'll sort of walk through lenses right now. Okay. Lenses and optics of the eye. Okay, so we have quite a bit to cover, so let's get started. Last week we talked about Snell's law, which showed us that we could represent light as a ray, just a single line with an arrow. And this is just the path that light takes, and we've simplified it to a line. That makes a lot of optics easier. That makes a lot of the calculations that we do just based on like geometry and trigonometry. We saw that from last week using Snell's law. So since it's been simplified, we've been able to understand lenses a lot more, and we can make this, simplified equation to describe how light can move through a lens, and that's called the thin lens equation. Thin lens equation. And if it's pretty much, if a lens is, thin enough, it's not traveling, through too much material, we could say that it goes through an object and then immediately changes its direction, and we don't have to worry about what it's doing inside the material. Let's write this equation out. So it's pretty much 1 over the focal length. So focal length is equal to 1 over the object distance. We can call that d sub O, plus 1 over the image distance, so d sub I. And I will go over these diagrams in a bit. Another thing we'll need for today is magnification. As light goes through a lens, maybe the image is bigger on the other side than the object actually is. So magnification is found by using this. So it's either you might see it as a capital M or lowercase m. Doesn't quite matter. Equal to negative. It is the image distance over the object distance. And this distance that I'm saying, so object distance, image distance, it's always from the center of the lens. So the lens is the 0 point. So object will be on one side of the lens, and most of the times the image will be on the other side. What else? This equation for magnification is also equal to the height of the image over the height of the object. So image height, object height. So you can use this. You can probably see how you could use this equation to get all sorts of values that you need. Object height, image height. A lot of possibilities. So let's get into these lenses. Let's see what they look like. There are two types that we'll cover. There is the convex lens. Convex. Also could be called the converging lens. This is the one that looks like a football or an oval. It's, larger in the middle. Like that. Okay. And here's the very center of the lens. Let me go like this. This line that I'm drawing is called the optic axis. So that is the very center of the lens. That's where we're kind of going to be making all of our measurements around. Okay, so there's the optic axis. And if you look at this lens, if I go right down the middle, the dotted line, see it's symmetric on both sides. So it's, round on one end, it's round on the other end. Because of this geometry, if you remember last week, however light hits a surface, that's how it will, dictate how it will bend. So since it's symmetric on both sides, that means there's a focal point that is equal on both sides. It's an equal distance. So be right about here. Pretty good. So that distance from where from the center of the lens to where light will focus. Let me, that is called the focal point, F. And it's the same on both sides, and I could just call them both F, but I want to keep things, easy for me to tell what they are. So I'm going to call the one on the right F. We call the one on the left F prime. And so let me do just a tiny sketch of one. So this is a converging lens. It's known to sort of take light and converge to a point. So I can put down, that's what I forgot to put, a little statement. So converging lens. Converges light to a point. Okay. So if I have a stream of light, coming in like this, completely parallel, it will go through the lens and converge. They will all converge at the same point right here. And that is the focal point. So where the light focuses to a point. Okay, so we have our two sort of little sketches. I'll do a more technical diagram in just a minute. So convex, the other type of lens is a concave or diverging lens. This type of lens will spread light out. Spreads light out. Okay, so this one is pretty much the opposite shape. It's large at the top and thin near the middle. See how well I can do this? Okay, that looks pretty good. Here is the optic axis. It's always going right through the middle, like that. And again, this lens is pretty much symmetric down the center, so it will have focal points on both sides of the lens. But let's put, one right there, and we'll put one right here. But since it's got a completely opposite shape, the focal points have been flipped. So this is F, and this one over here is F prime. And this line, again, is the optic axis. So a diverging lens, let me do just a little rough sketch down here. A diverging lens, if there was this stream of light coming in, you're just shining a flashlight on it, we would expect that the light coming in would then spread out in all different directions. Okay. So that's what we expect from these types of lenses. Let's make a more technical, or I guess, slightly technical ray diagrams for these. So let's put that there. I got enough space. Okay. So convex lens, let's do that. Okay, so we have a lens that looks like a football. And it's not, I didn't draw it the best, but let's say it's symmetric. Okay, there's the optic axis, and it has two focal points on each side of the lens. I'm going to say one's right here, and one is right here. They should be the same distance away from the center of the lens right here. Okay, so one of them is F prime, one of them is F. So we expect if light were to come in, it will go to the focal point right here. So let's make an object on this. Let's put an object in front of this lens, see what happens. Okay, let's put a candle. Some people put like an arrow. I want to do a candle. So here's a candle, and it's placed, a bit far away from the lens. Here is where it's positioned, right here. And this distance from where it sits all the way from the center of the lens, that is the object distance. I don't want to keep all of these lines in here, so I'm going to put that just like that. So that's where it sits. Okay, so I'm also going to put how tall the object is from, up here to there. That is the object height. But again, I don't want too many lines. This is going to have a lot of lines on it in just a minute. Okay, so how can we, just put a dot up there for reference. How can we draw this ray diagram? Well, there's a few steps that we can always do whenever we have to draw one of these. I don't know if you guys would have to draw one for a quiz in your lecture. You might have to. Let's go over some steps. So step one, how to do a ray diagram. You can go from the top of the object, go from top of object straight through the center of the lens. This is going to have to move down a bit. What about there? Okay, so that's why I have this dot up here. Go from the top of the object, and I need to put a ruler, or like a little this. So go from the top of the object straight through the center. So right here, the center of the lens. So here is our line. Nope. That was an eraser, go like that. Okay. So it went from the top of the object straight through the center of the lens. That's step one. You could always do that. Step two, here's something. I'm going to underline this because we're always going to start from the top of the object. So go from the top of the object. Go parallel to optic axis. Then go through focal point F. So go from the top of the object, go parallel to the optic axis, then go through the focal point F. So let's go parallel to the optic axis, like this, until it hits the lens, and then go through focal point F. Okay, so that's that. And I don't have any measurements, so this could probably be a lot better. if I was using an actual ruler. That's the cool thing about these diagrams, is that if you do them accurately with a ruler, you can get actual values just from the drawing. Okay, so that's step 2. Step 3. Go from the top of the object. Go through. Go through focal point F prime, then go parallel to optic axis. Okay, so go through F prime, so that will be something like this. And if, say, I didn't draw the lens big enough, I could just redraw the lens a little bit bigger. Yeah. And just imagine it's going through this dotted line. Right when it passes that dotted line, now I have to go parallel to the optic axis. So that would look like this. And this is going to be pretty good. This is the best one I've done so far. And we can see they all converge at one point right here. So let me make a dot right where that is. So right there. So what does that mean? That means that this object is projecting an image on the other side of the lens that is upside down. So it's going to look like this. And that's what it looks like. So I would say this image, let me put it right here. So I would say the image is inverted and I would say since image is on the same side as the light rays, it is real. If you haven't heard that, you know, vocabulary before, it might seem a little weird to say that this image is real. There are going to be what are called virtual images, and I will do that one next. So this is going to be the distance. I should have left just a little bit more room. This is the image distance. Let me shrink that so like right there. So this is the image distance from here to the center, and this is the image height. And since it's inverted, we'd see that as a negative value. Okay. See how much time? Okay, we're still good. Let's do I'm going to leave the steps. Actually, I'll just go like that. Now let's do the concave lens. That one, just very quickly try to get one of them. That's pretty good. Looks like an hourglass. There's the optic axis. Since it's symmetric about the center, we'd expect two focal points. Say one's right there, and we'll say the other one is right here. However, the focal points have been switched. So this is F prime and this is F. Let's put an object right here. Same thing, it's a candle. And it is at the object distance, D sub O. Good thing is I don't have to rewrite those steps. I could always use those steps. So I could go from the top of the object straight through the center of the lens. That'll be right here. Okay, so it would look something like that. Okay, step 2, go from the top of the object, go parallel to the optic axis, then go through focal point F. So let's go parallel to optic axis. Now we've run into a problem. Focal point F is back the way I just passed over it. So how does it, get there? Well, this is where we have to connect it with a dotted line. So let's connect this point right here to focal point F with a dotted line, but then let's keep continuing that line as solid on the other side. Here's what I mean. So I'm going to connect it, the dotted line, and then on this side, on the right side, I make that a solid line, straight out like that. Okay, that's kind of what we'd expect from a diverging lens. It spreads light out on the other side. Okay, and step 3, go through focal point F prime, then go parallel to the optic axis. So let's line up the top of the object and F prime. So I'm going to go like that. Oh. Go like that till I hit the lens. But now I have to go parallel to the optic axis because I'm going through the lens. So let's go parallel to the optic axis and continue that this way. So where does this light ray, make that image? We see I have this solid line over on the right. It's creating this arrow that way. I then continue that backwards. So let me take that same line and make a dotted line that goes backwards. And we can see it's almost just missed, but there's this point right here where these dotted lines converge. These dotted lines, they're not actual light rays that come back to make this image. It is it's just like if we were to put something there, it would create this small virtual image. Let me put the dot first so you can see. So it's like right there. So this is a very small image of a candle that would appear, but there is no light sort of creating it. Yeah, that sounds kind of weird to say. I would say this image right here, D, so I. So I'd say this image the image is, well, it's, still, pointed upwards. So I'd say this is upright. And I would say since image is not on the same side as the light rays, it is virtual. Okay. How do I? Okay. Just a bit more things to cover, and then I'll get you guys started. You probably have already started, but we'll continue this anyway. So last final thing, optics of the eye. I'm not going to do many like diagrams or anything. I think the instructions walk you through it pretty well. Let's go over sort of a normal eye. Normal eye is the eye. It has that lens in it. And in your eye, there's muscles that will squeeze and stretch that lens that's right in the front. Squeeze it together just to change its shape. And after a while, I don't know if you guys have ever like been reading too long or holding something too close to your face for too long, but your eyes can kind of get strained. They sort of feel tired. There's these muscles trying to hold this lens at a specific shape for too long. So let's see. Let's go like this. For a normal eye, there is this sort of limit on what you can see. I don't know if any of you have 20/20 vision, but this also applies to other people, pretty much everyone. There's a point where you guys have writing around you, like a page with writing on it. There's a point where you could hold something up to your eye and you physically can't focus on it anymore. There's a limit on how close something can get for your eye to be able to focus on it. So that will be right about here. And it's called the near point. So that means that once you get to that point and anything closer than that, so anything in this region is blurry. Okay, and for a normal healthy eye, 20/20 vision, this eye can see pretty much infinitely far away, as far as it's able to see, for the environment. It has a far point, all the way out at infinity. Okay. So that's for a, I would say normal eye. I think it's normal for people to have something going on with their eyes. For an eye with 20/20 vision, I'd put that here. Okay. Let's look at two types of other eyes. For nearsighted, there's nearsighted eyes. Nearsighted. I've always been confused with this. Nearsighted is just can only see near. All right. For people with these types of eyes, it is just it comes down to just the shape of your eye makes it hard for you to see something far away. So I believe I'd have to look this up. I might get these reversed. I believe nearsighted eyes, you have sort of these really long oval eyes. Let me make that a little like that. So it's not a circle, it's more of like a stretched out ball, like a rugby ball or something. And so for that normal eye, let's do that little picture one more time. So for a normal eye, light will come in and converge at the back like this. It's a bad picture, but I think you get it. So for this nearsighted eye, it's your eye is just too long. You'll go in, hit the lens, but no matter how that lens bends and stretches, your eye just can't, focus on the back of the retina. So these people have nearsightedness. Let's go, and I'll do this same type of diagram. So they can only see near. So that means they have the same near points. Probably near point is about the same. Still pretty close. Everything closer than that is blurry. But that far point that was at an infinity for someone with 20/20 vision, that has been brought in significantly. So it's not at infinity anymore. It can be now actually measured, and it can be, say, like right there. So now that is their far point. It's not an infinity anymore. So then anything past that is blurry. So they have this very narrow range that you could see within. And the far point is different for, each person with nearsightedness. Because everyone's eyes are physically just different shapes. Okay, let me do one more and then we'll be done. For someone with farsightedness, farsighted, they can only see far. I believe these people, again, I might be getting these mixed between the two. I believe their eyes are flat, sort of like a pancake. Make it a little bit more like that. Okay. So if I was to do the same sort of diagram as this, it's your eye is too short for your lens to, bend and stretch to focus on the back of your eye. So light will come in, but it converges back here. And that means it doesn't focus on the retina on the back of your eye. Okay, so doing this diagram, for someone with farsightedness, they might have a far point out and fit out at infinity still. So they could see everything far away. That's fine. But that near point that was, a couple centimeters in front of your eye, that has been pushed out a lot farther. So now their near point is right here. So they have this much larger range right in front of them that they can't see, and all of that is blurry. Okay, so you might see terms like near point and far point. I was just hoping that these help with that, so you know what it is. Okay. Are there any questions on the notes? We went over a lot. I will clean these up and put them up later, like with the video and all that too. Yeah, if you guys have questions, let me know.